Okay, I'm going to continue the discussion of single mode fibers. Here we are in Chapter 5 with a discussion of leaf and vascade fibers. In the previous slide I've shown a summary of the single mode fiber types, and I've discussed the SMF28 varieties, and I've also discussed the clear curve. Now I'll talk about leaf and vascade. Before I talk about leaf and vascade, though, I need to introduce two important concepts. The first one is dispersion shifted fiber, and the second one is nonlinearities. We've seen the step index fiber, and we've seen, well, here's a picture of the index profile of step index fiber. So at r equals 0 we have the center of the fiber, and it's symmetric about r equals 0, and we have index N1 in the core and index N2 outside. We saw that the dispersion in picoseconds per nanometer kilometer is the sum of two different terms for single mode fiber. It's the sum of the material and the waveguide dispersions. Okay, the material dispersion is generally much larger than the waveguide dispersion, and I've shown it just schematically here for the range from 1100 to 1600 nanometers. The material dispersion has a 0 at 1300 nanometers. The waveguide dispersion has the opposite, is positive throughout that region and quite small. But when you sum the two, you get this red curve for the total dispersion, and the waveguide dispersion tends to push the zero dispersion point for the fiber out a little bit above 1300. Okay. The neat thing is that if you engineer this index profile, and here I've shown just a couple of examples, if you engineer this profile, and for example, play some games out just outside of what would be the normal core, you can cause the waveguide dispersion to go up dramatically. Okay, and if the waveguide dispersion goes up dramatically, it's possible to move the zero dispersion point for the fiber, that is M total, all the way out to 1550 nanometers. And that's a great thing. That's called dispersion shifted fiber, DSF. And that's a great thing, because then if you send 1550 nanometer light down this fiber, you'll have very low dispersion. Even if it's slightly off 1550, you'll have very low dispersion, and your bandwidth distance product goes up substantially because of that. Okay, so we can engineer the index profile to shift the zero dispersion point of the fiber. And let me just show you quickly that in your textbook, the diagram for the material dispersion is given in figure 3.8 on page 69, and the diagram for the waveguide dispersion is given in figure 5.25 on page 150. Okay, so that's the idea of dispersion shifted fiber. It turns out that shifting the zero dispersion point right to 1550 isn't always the greatest thing, and I'll show you why now. And the reason is nonlinearities. Okay, nonlinearities means that at very high intensity of the light, the refractive index depends on the intensity itself. Okay, and so this has a big effect on two types of systems. First of all, it has a big effect on WDM systems, where we've got lots of wavelengths simultaneously in that optical fiber. And so, for example, in a 40 wavelength WDM system, we might have 40 times as much light in the fiber, just thinking about it, as you would in a single wavelength system. The other place where nonlinearities often have a big effect are in submarine systems and long haul systems, but especially submarine systems where they really have to go a long distance before they can regenerate or amplify the signal, and so they pump as much optical power into those fibers at the launch as they can. Okay, and nonlinearities really creep in. So this is the first type of nonlinearity at large light intensities. Refractive index depends on intensity. There are three effects of that. The first one is called self-phase modulation, and basically, if you have a very strong pulse, it sort of modifies itself. The strength of the pulse changes the index, and that varies. That in turn causes an effect on how the pulse propagates. The result of that is that we have an increase in total dispersion for that pulse. So we have a self-phase modulation, an SPM component to the dispersion in that case. That's not really the one we're worried about. What we're worried about is cross-phase modulation. In cross-phase modulation, when you have a WDM system, you have lots of lambdas, lots of wavelengths or wavelength channels in that fiber. It's the pulses from the other wavelengths which are causing the additional dispersion to your pulse. And it turns out that this only happens when those wavelengths sort of travel together for a long distance through that fiber. The only time when pulses of different wavelengths will travel together through the fiber is when the dispersion is about equal to zero. Okay, so in other words, we need to keep the dispersion away from zero in WDM systems, or else cross-phase modulation is going to distort our pulses and decrease our bandwidth distance product. So what they do is they make what's called non-zero dispersion shifted fiber, NZDSF, where we've got low but non-zero dispersion at 1550. Okay? And in fact, that's what leaf fiber is. Leaf fiber is non-zero dispersion shifted fiber, and this is from some internet source, I believe it was opticsforsale.com, showing the index profile of leaf fiber. It's sort of a funny triangular shaped index profile. Okay. And so let me move on to the third effect that the refractive index, depending on the intensity, can cause, and that's another one that occurs in WDM systems. And in this effect, we have multiple pulses of different wavelengths, and I'm calling them frequencies I, J, and K here, in the WDM system. And it turns out that when you have the three frequencies like this, there are sums and differences. There's a large number of terms varying the pluses and the minuses here that can give rise to a fourth frequency, and that's why it's called four-wave mixing. So it turns out that energy is transferred away from those three frequencies I, J, and K and into this frequency F4, of which there are many. And again, you can avoid this by keeping the dispersion away from zero, and that keeps the pulses from traveling together. That keeps all these different frequencies of pulses from traveling together for a long distance. In other words, what we say is that the pulses walk off from each other because they're going at different speeds. Okay, so that's the first class of nonlinearities, where we have the light intensity affecting the refractive index. The second class of nonlinearities is when we have scattering effects that cause power transfer away from the pulse that we're interested in studying. So we have a pulse and it loses its power through two different mechanisms. The first one is stimulated Raman scattering, where and this is applicable to WDM systems, when we have multiple wavelengths in the fiber, power in a pulse is shifted to the pulses with longer wavelengths. Again, avoided by keeping the dispersion away from zero. When the dispersion is zero, all these pulses go at the same speed, and they have this opportunity to shift the power. So keeping the dispersion away from zero means that we have pulse walk-off. Okay? And this is exactly what happens in non-zero dispersion shifted fiber. The other effect of scattering is stimulated Brion scattering. Energy in the pulse is scattered backwards in the same fiber at the same wavelength. We're not so interested in that one. By the way, though, Raman scattering can give rise to a very powerful class of fiber optic amplifiers called Raman amplifiers. Okay, so just to wrap this up, non-zero dispersion shifted fiber has its zero dispersion point shifted out into the 1550 range. I think it's usually a little bit above 1550. And that way, in this range of wavelengths from 1530 to 1575, where WDM systems, 1550 WDM systems typically operate, we have low but non-zero dispersion. So we get the best of both worlds there. We get low dispersion, but we don't have zero dispersion. And that's exactly what leaf fiber is. It's a non-zero dispersion shifted fiber. It also has a large effective area, and that's a result of that triangular index profile in leaf fiber. And what the large effective area does is it keeps the mode field diameter larger than in a normal single mode fiber. It therefore reduces the light intensity and reduces the nonlinear effects. So leaf fiber has two things going for it: large effective area and non-zero dispersion shifted. Just to finally wrap it up, Vascade fiber. If you click on it on the Corning website, there's a lot of different varieties of Vascade. Very complicated, but generally non-zero dispersion shifted fiber for submarine use. It's also got some sort of strengthening in the sheathing, so it can be pulled without breaking. Okay, thank you.